Okay, today we're going to be looking at continuous random variables. So, we've already met continuous random variables, but we've actually been doing quite a bit of work on discrete random variables. But let's first think about doing experiments. Oops. We're always going to get errors in our measurements. If you consider if you were having to measure the length of, say you had so you're doing a biology experiment, you had some earthworms. I want to measure their length. If you think about the actual length of these worms, you can take to ever increasing degrees of accuracy, well, within the realms of what's possible to measure, and you're never going to get that measurement completely right. There's always going to be error. So to compensate, we take many readings and then take the mean. So let's say we had our graph of, this would be our frequency, and this is length, and say we were measuring this earthworm and we're repeating it, you'd probably find a graph a bit like that, where there's a degree of error, and then this would be the mean value, and this would be the value we took for the earthworm. And sometimes you would underestimate, sometimes you would overestimate, but these over and under values that you've measured, these erroneous values that you've measured both below and above the mean, they cancel each other out. And so the mean value is going to be a pretty good and accurate reading for the length of our earthworm. Now, Carl Friedrich Gauss was a famous mathematician, and he discovered that when studying errors in scientific experiments and also in astronomical calculations, observations, he discovered there was this distribution around the mean was something that kept propping up, and he called it the normal distribution. And this is what we're going to be studying in this final chapter. And the normal distribution has this mean, and it's symmetrical about the mean. So let's just quickly define again what a continuous random variable is. So it's a variable that can take an infinite number of possible values. So we've been looking at discrete random variables, and they're like, if you roll a dice you can only get 1, 2, 3, 4, 5, 6. A continuous random variable can take an infinite number of values. For example, the height, measuring height of a population, it can take a continuous range of values. Say you were taking the mass of an orange. This is our orange. And we've got lots of oranges, and we measure the mass, and we say this is X grams for the mass. The mass would be between some values of A and B for the mass, because it's a continuous random variable. So we were looking at the probability of a discrete random variable, and that was when we random, and we'll call it x. So we denoted that as p is x when x is for some value of r. But for a continuous random variable, we represent the probability as p between some values, a range of values of a less than or equal to x less than or equal to b. So with continuous random variables, we've got this range of values, and we've done this before. We've looked at this before. And to study these, the probability distribution of continuous random variables, we're going to be graphing them. So we want to find a representation of the probability distribution. So what we do is we have a set of continuous data which we represent as a histogram, where column areas are proportional to the frequencies of which those ranges occur. And then we draw a graph based on the data. So say we had and this is y, and this is our probability density, and we have our histogram, so it's going to go up like this. This is quite a rough histogram. And then we draw our graph to the shape of our histogram. Now if we change the frequency density values on the vertical axis to relative frequency density, so the relative frequency density is going to be equal to the relative frequency times the, divided by the class width. Then the column area will represent the relative frequency. And these relative frequencies are estimates of the probability. And so when that's the case, the vertical axis would be probability density, which we've got here. The width of the class intervals, for the width of class intervals, so this, what we've just done here, doesn't change the shape of the diagram. So the shape of the diagram doesn't change. And if you were to take the sum of all the frequencies, it would equal 1. So the area under this graph is always going to be 1. Let's just get a fresh page up. So in the case of a random variable, so say we have the curve representing the probability density is going to be y equals some function f of x, and this is called the probability density function, or PDF. And the area is always under the probability density function is always equal to 1. So let's look at a couple of shapes. So this is our probability density. I'm just going to draw the shape, and then I'll draw the histogram underneath it. So imagine a histogram here. These are meant to be equal widths. So this curve is y equals f of x. This is the probability density function. Now we can have something else. And I'm going to draw one that's kind of odd. So here's our histogram. Again, their widths are meant to be equal. And this curve is y equals f of x. Now, this looks like nice and normal, and this looks all odd. And we're going to see that this is in fact a normal curve, and this one actually isn't. Now, the function, so y equals f of x, it's important to define that can only be used when referring to, let's rewrite that, to the random variable. For the data, we should rather say the curve or the graph. Let's just to mention that there. Now let's see some 3 common curves that we'll see if you do analysis of random variables, of continuous random variables. So let's do it again. Something like this, or you could get something like this, or you can get something like this. So this is our symmetric curve, and so the tails off here are both even, and this is one that we're going to be looking at in a bit more detail in a minute. It's called the normal curve. This one here is negatively skewed. So it's got a longer tail to the left, and this one is obviously positively skewed. So it's important to be able to recognize these different shapes. The mode is the graph's peak, and the median is the value under the graph. Is the value at which is the value at which under the graph the area is half. So if you think about the area under all these graphs is going to be 1. So let's look at the negatively skewed one. This is going to be the mode here. But if you were to look at the area and half the area between this area and this area, that area there is not equal to this area here. So the area would be kind of skewed off to this part. So this value here would be the median. And likewise on this one, oops. So this here is the mode, this peak value, and here would be the median, roughly. And for the symmetric graph, the mode and the median are at the same value. So let's think about the normal curve in more detail. So the normal curve takes, this value. So this is the probability density. And it takes this symmetric form. So, and it's this typical bell shape. So in a normal curve, the characteristics of it are that the mean and the median and the mode are all equal, and so it'll be this value here. So this is the mean. So that's the peak value. The probability density decreases as you move away on both sides of the mean. And if you have an increase in standard deviation, and the symbol for standard deviation is this one here, a small omega, the graph becomes more spread out. So let's look at that let's look at a few different shapes. So we've got our axis, this is probability density. I'm going to change the colour, so we've got two different curves on the same graph. So let's do red one. And let's do a green one. So we've got, for both of these, our mean is both the mean of, so I'm going to call this is graph A, and this is graph B. So the mean of A is equal to the mean of B, because they both have the same peak at the same place, but this one is more, A is more spread out. So the standard deviation of A is greater than the standard deviation of B. Let's look at another example. This time we'll have a graph. Here, now these are meant to be the same shape. So this is B and this is A. So this time the mean of A is less than the mean of B, but the standard deviation of A is equal to the standard deviation of B. And always remember that the area under the normal curve is always 1. So the area under the normal curve is always equal to 1. It's just the shapes will change, but they all have the same area under them. So I hope that makes sense.